welcome back if you're, well, both in the live audience here and also on live stream. And I'm pleased to introduce our second speaker of this afternoon, Ralf Herbrich. Ralf did his PhD at the Technical University of Berlin. I believe he joined Microsoft Research in the year 2000, went through a number of different kind of roles in Microsoft Research, working in applied games and online services and algorithms. Then in the, it's hard for me to read this right here. Okay, the future, let me see, future social enterprises, is that right?
Experience.
Okay, future social experiences.
Facebook.
Okay, before moving to Facebook for a short time, about 1 year. And then since 2012, he has been at Amazon as Director of Machine Learning, first in Seattle and now in Berlin. I think, let me not spend more time, let me allow you to hear Ralf talking about probabilistic models in real-world applications. Thanks.
Thanks a lot, Chris. So yeah, it's really quite exciting to give this presentation. And what I will let's see if I can get this working. What I'll do is I will talk about algorithms that kind of work on it's a continuation of the talk from Tim. Algorithms that work and require this distributed thinking and the distributed hardware or assets that support this that come from machine learning. And more specifically, algorithms that deal with uncertainty that arises when machines make inferences from data. So there's 3 parts, and it kind of reflects a little bit the places I've worked at. I'll start with a bit of theory, a bit of background on one of the mathematical models that allows to really link between a statistical description of a problem of data and one of how to translate that into computation. Computation that then also needs to be distributed. So the 2 key pieces is the data structure. It's a graph. It's called a vector graph. And an algorithm on vector graphs called approximate message passing. So I guess after 15, 20 minutes, it might feel a little dry. So I try then in the next 20 minutes to make it a bit more applicable. So what I want to talk about is applying exactly those algorithms I'm describing here to 2 really large-scale applications. One is for a problem that many of you can and have tried out, which is matching people together that want to play online against each other based on their playing strength. So how strong are they in racing at the same speed, or perhaps playing a first-person shooter, or playing a tennis game, or a golf game, or any kind of virtual gaming activity you can think of. And the second one is, I'm actually also going to present, if you reapply this to one of the earliest games, not Go, which is quite popular these days, but chess. And if you apply to chess, what would be the outcome if we were to make inference on such a model across a time span that goes beyond the life of a single human? In fact, 150 years. And in the second part, applying it to something that is also quite practical, some problem we worked at Amazon, which is to infer how many pieces of fashion, jackets, shirts, shoes, jeans are demanded, are asked for in individual marketplaces, where you have a lot of uncertainty in what the future looks like, because you go all the way to 6 months into the future. So you need to deal with uncertainty from a machine learning point of view, and you have very sparse data. So the kind of data time series you look at there have very, what we call intermittent demand, meaning a lot of the items you can buy in shops and in Amazon are not selling in hundreds every day, but probably more in single digits every day or even less. So as I said, the basic mathematical tool we're going to use is a graphical model. And what is a graphical model? I got introduced to it first around 2000, and took me a while to grasp it. So the best way I understood it is actually just a picture of a probability distribution. So what that means is that every variable in the probability distribution comes a round little circle, a node, and every edge between them represents a form of relationship. So what is a variable? Well, there's 2 things really that can be a variable. Something I recorded, which I call data, and something that causes the recording. I call it a bit, loosely speaking, a cause. It's not really a cause. It's more like what we call an effect model. A latent, non-observed variable that here's a relationship to data observed. And so when graphical model got first introduced back in the 90s, the key question that people wanted to answer from a picture is conditional dependency, because it was used in modeling. So the question of, if I have a joint, if 3 little round nodes represent a probability distribution over 3 variables A, B, C, can I infer by looking at that picture if A is independent of C? Can I basically answer the question that any function, that's a probability, will factor over A and B? So that was the initial question. That's important for modeling. What's important for learning is a different question you want to answer, and that is the question of marginalization. So the idea of saying, well, I used a bunch of latent variables. So in this case, very simply, I used one C that I needed to describe the data observed, but I'd like to know everything there is in the data about A and B, and the best way to do that is you just sum out all the variables that you're not interested in. Simple operation, unfortunately, you'll see this is quite a complex operation when you apply it in a stacked way. Good, now the one representation that really is quite powerful, and it's very simple to go from one to the other, is a vector graph. So the vector graph has a slight twist to it, that you're not just having round nodes, you also have square nodes, and the square nodes are the vectors. And now every variable is only connected, every round node only has neighbors that are square nodes, and every square node only has neighbors that are round nodes. We call this a bipartite graph. And the meaning of such an edge is simply that every factor that is connected to a variable is basically, every variable that's connected to a factor is the set of variables that factor involves, and the whole notion of the vector graph is that it denotes a product. So this graph denotes a product of 3 factors, one factor that only involves A, one factor that only involves B, and one factor that involves A, B, and C. So that's the simple semantic of this picture. So you look at that picture and you basically see a product, or you should see a product, and you should see the local dependencies of each of the individual factors. Now, why is that important? Well, one importance you can see when you think of the statistical tool to make inference known as Bayes' law. So Bayes' law says, in fact, is a vector graph. It says that the knowledge that a machine has, for example, over the skill of 2 players given the match outcome Y, is proportional to the knowledge, the likelihood that a match outcome realizes given the skills times the knowledge that the system had over the skills. And I assumed 2 skills now, so one easy way to, this is the vector graph. You have 2 factors, factor 1, factor 2, and you have 2 variables. One is actually observed, little gray, one is not observed. Well, one way we could sort of split this up, say, let's store the skills independently in independent registered or memory addresses. So that means we're factorizing the skills. If I put this in a picture, very easy to see. Now I have individual memory cells that store what the skills are. I happen to have now 2 factors for each of them. Now, in order to describe how the match outcome results, I need a few more variables. And one of the simpler models, we're going to come back to it, is to say, well, the skills are influencing the performance of each of these 2 players. It's another factor. And the performances influence the difference in the performances. This is a very deterministic operation. It's simply just the difference of the 2, but it's still, you can express it as a delta P distribution. And the difference being positive means that player A1 wins. The difference being negative means player B wins. So what we see here is now a much richer vector graph that describes the generative process of getting a match outcome from a set of skills. Now, as I said, there is in order to describe this generative process, we kind of threw in a few variables that we needed for modeling, but we don't need them to infer by an algorithm what are the skills of those 2 players after the first player won. So the operation we need to perform is so we have a joint distribution over the performances and the difference in performance. We need to sum out those 2 variables. So in this case, T1, T2, and D. And the naive way of doing this is just 3 nested for loops. So we just sum over all values of T1, sum over all values of T2, sum over all values of D, and then we're done with it. We're basically, if these are binary variables, have 8 operations to perform, and each of them it's a product of 3 factors. Now the nice thing is that, so I took the same thing, I turned it 90 degrees around. There's actually an efficient algorithm you can do that simply by looking at that picture. So for the rest of the talk, I should say that blue is always algebra, black is always picture. I understand pictures better, and that's the whole point of our graphical models. So suppose, for the sake of explaining the algorithm, we wanted to work out the marginal of W. So that means we sum out V, we sum out X, Y, and Z. So if we were to do this, how many operations would we need to perform here? these are these are sort of variables that have two values only, right? One for loop, one for loop, one for loop. Another has 16. So with 16 summations and each time doing a product of 4 values, we can work this out. That's the naive implementation. One thing we see though is a very simple rule of algebra reduces the number of operations significantly, and that is the distributive law. So distributive law says that A times B plus C, parentheses, equals A times C plus B times C. So A times B plus C is exactly how many operations? It's 1 addition, 1 multiplication, so that's 2 operations. A times C plus A times B, it's 3 operations. So if we apply that law the other way around, we go from 3 operations to 2 operations. So let's just apply that simple equality, and the funny thing is that equality also holds for max. So not just for summing things, but for maximizing things. So if we apply that, we can already break this, reduce this from 16 summations to a smaller number, because this term does not depend on x, y, and z. Right? This depends only on w, of course, and on v. So we can apply the law that I just described the other way around and pull that factor out. So if we pull that factor out, how many operations have we got left? Well, let's count. We have 2 summations here. Then we have 2 times 2 times 2, so we have 8. So we're at 10 operations. And then we have 1 more, 11. So we're already down from 16 to 11. So that's why are we down from 16 to 11? Because we exploited the structure of this graph. Pictorially, this is very easy to describe. We basically decomposed this big sum into a product of 2 partial sums. One sum over all values of v, and one sum over all values of x, y, and z. And if you think of it as a picture, all we've done is we've just reduced the summation around all the neighbors of that variable. So the simple rule is, if you have a sum of products, this was a sum of products, it becomes a product of sum, the same way that A times B plus C becomes A times C plus B times C, or the other way around. And if you do it in a vector graph, then you just need to take the partial sums from the neighboring vectors. So if we give a name for these partial sums, this is still a function. Even if you sum out v, it's still a function of w. Even if you sum out x, y, and z, it's still a function of w. We end up with a simple equation that says the marginal is the product of all partial sums. Let's call these things messages. We'll see in a minute why that is a clever way to name them. Messages from the neighboring vectors to that variable. Okay, strip the left part off. Let's look at the right part. Can we do any simplification here? We can. We can use the same rule just once more. Because for F2 only depends on w and x. So we can pull that out. In fact, in order to perform this big sum, we only need to perform the sums over the variables that this vector is connected to. So before we had 8 operations, right? For loop, for loop, for loop. And now we have 4, 2, 7. It's not a huge reduction, but some reduction. So we got down to 7 operations. So if we do that, we see the second rule, which is of the vector graph algorithm. Every message, the partial sum, every message from a vector to a variable is defined by summing out all the variables that are connected to that vector as well, weighting by this thing. Now what's this thing? It's a partial sum. This is still a partial sum of x, right? X is the neighboring variable. So what comes from this variable x is a partial sum, is a function of x, and it's basically this whole thing summing out the value of x. So strip that off. So now we're left with this simple sum. So if we perform this one, we see one thing, which is the message from a variable to a vector can be distributed into this summation and this summation. Or input in algebra, this sum is basically the same as the product of these sums. So we recursively apply the distributive law. And this is true for, I showed it for sum product, it's true for max product as well. Now, so we could give this a name because we have already defined these partial sums. These partial sums were messages from from vectors to variables. So if we put these 3 pieces together, we get this very simple algorithm. And you just saw how I peeled the tree off. I just picked the node and I peeled it off. So the peeling off is you pick a variable, then you just have to look at the neighboring vectors. In order to get those, you look at the neighboring variables. And for the neighboring variables, you look at the neighboring factors. And then the recursion ends if it doesn't have a loop. So the update equations are directly derivable from the distributive law. The other nice thing is, once we have all the messages computed, and how many messages did that graph have? Well, only as many messages as there were edges. And that's where the reduction comes from. If we had all the edges in this graph, then we're back to a fully meshed graph. We're back to the same computation we had to do before. So we're now down to a calculation that takes no more complexity than just the number of edges of that graph, rather than the number, the exponential in the number of variables in that graph. And we only need to do this computation regardless of which variable we're interested in. We only need to do 2 computations per edge, the message from that variable to the neighboring factor and from the factor to the neighboring variable. And then we can compute any marginal of this graph, and the machine can answer any question about any of the latent variables, whether it's the skills, the performances, the differences. They're all encoded implicitly by those messages. What's nice is also, it's when you look at the 2 rules, so these were 1 rule, the marginal of a variable is the product of all messages that come to this variable. So that's this. So this marginal is sort of that full product. And the message from the variable to the neighboring factor is the product of all those. Okay, so the marginal, I multiply all 3. And for the message that goes out here, I multiply those 2. So that means I can pick any neighboring pair of variable and factor. And it's true that that message, this is the missing red arrow, times this was all the others. Even if there's a million factors connected to this, we'll always make the marginal. Okay? So just some pictures again. The marginal was all 3 arrows together. And the outgoing one was all the other arrows except the one I travel along the edge. So this is important for computational reasons, because that means if you actually implement that, what you should do is only store the marginals and only store the messages from factors to variables. The other ones you can always compute by division. You can always compute this message from a variable to a factor by this divided by this. And if these functions are exponential functions like a Gaussian, a Bernoulli, a Poisson, a beta distribution, a binomial, a gamma, like a lot of distributions that you know from textbooks, this basically comes down to dividing 2 precisions. Subtracting 2 precisions, or dividing 2 log odds. Subtracting 2 log odds. So these are very basic addition multiplication operations. Now, here's one catch. It will be beautiful if we could just perform that, but if we look at those equations, here's the catch. So let's just go back. If this is an exponential, then the product of one exponential stays an exponential. If this is an exponential and the product of an exponential stays an exponential. If this is an exponential, so Gaussian, but this is an arbitrary function like a threshold, this is no longer a Gaussian. Right? Let me just show you in pictures what the problem is. So in pictures, the problem is if this is a Gaussian, and so assume that we've modeled skills that a machine has or believes as a Gaussian, and now I just said if the difference is positive, player 1 has won, we literally have to multiply the blue function, this was the message from the variable to the factor, by the actual message, by the actual data equation, if you wish, to that variable. And what you get is a nice truncated Gaussian in the case that this is a threshold function. So the idea and the great insight that Tom Minka and I guess a lot of others had at the time is to say, well, why don't we approximate this thing? Because that's what we're interested in. We're interested in the marginal. We're interested to the machine to answer the question, what is the skill? Or what is the performance difference? Or what is the latent demand? So why don't we approximate that back into a Gaussian? Because if we have a good approximation for that Gaussian, then we can easily compute the best approximation for the actual data factor. Because it's the black function divided by the blue, and dividing 2 Gaussians, as I said, was just subtracting 2 precision and subtracting 2 precision means. So if you do that and you plot it, you get this wonderful function. Now, it looks like a terrible functional approximation, but bear in mind, this is a proxy. This is just sort of an intermediate variable in order to compute for the machine to actually compute the belief over skills, demands, and quantities you're interested in, effect strength. Good. Now, how does this relate to distributed algorithms? First thing is, why do we need distributed algorithms? And here's a few numbers. Actually, some of them might be outdated. I think definitely the first one is a bit outdated in light of recent announcements. If we look at Facebook newsfeed, so they rank all the stories in Facebook according to the predicted relevance, which is learned from data. So you probably have in the range of 100 billion news stories. The number is actually more in the trillions now. I mean, there was recently a blog post that said every average Facebook user has 1,500 stories that need to be ranked and looks at about 300. So let's say it's 300 you get data on that they looked at and clicked on it or not. And you have 1 billion daily active users on Facebook. So you have 300 times a billion, so 300 billion examples per 24 hours. You look at Amazon's forecasting problem, there's more than 30 million products that get ordered per day, so there's a lot of data per day. You have to, this is data you learn from, you have to learn from over 20 million products what is actually the demand. The problem is, you think, well, I'll just buy a big computer with a lot of RAM, so I get the latest Amazon Web Service instance with 2 terabytes of RAM, and I just run my algorithm. Well, the problem is that the day's only got 86,400 seconds, and it does take a little bit of time to write to memory, as Tim was just alluding to. And unfortunately, it also takes a bit of more time to even write to memory, a little less time to read from memory. So you need to parallelize, because you divide those numbers, 10 to the 13 doesn't hit the amount of changes of parameters that you would need to do. So how can you use this vector graph framework for that? Well, one nice way to do that, and here's a very typical graphical model for the assumption that you have parameters that govern your data. So these could be skills, or these could be strength of effects that a particular day in the year has on buying behavior of a product. And you say that these parameters govern that are observed. Player 1 wins against player 2, or they kind of are the functional model, likelihood model, that drive the demand on a given day. So, if you were to factorize them, then you see that connectivity pattern, like which parameter affects which particular observation. So look at the graph this way. This is actually only communication that ever needs to take place. In fact, the data model, what effects are relevant for which observations, govern how you should distribute both the computation, because this data of this scale doesn't arrive on a single computer. Data of this scale arrives at several machines. But it also governs how you should partition those particular, if you have large models, those particular variables. If you can't store them, can't store them in a single machine. And then the connectivity pattern very much determines the strategy that you use for distributing the workload, as Tim has been explained in the last talk. And here's one such. I think it's very similar to what Tim described. One idea to do that outlined here is if you have many machines that are basically handling subsets of your data, you have a cache of the actual parameter in those nodes. So you hold those parameters that are relevant for the chunk of data, for the blue box, for the red box at the bottom, in a cache here. And then you have the true values in another set of machines that are also partitioned. This could be, even if your memory is large enough, you do need isolation here in order to benefit from parallelization. And you only run the communication this way, but you basically send the actual message across to the service. So if this goes across a fast wire, then that will take some time. So what happens now is that there is a need to actually update that cache. And one way that in machine learning algorithms, this is known as a parameter server. This is known as a data server. So there's literally a lot of literature on parameter service implementation. One way to keep these two in sync is that you perform an estimation on this side, on each of them, how fast is the rate of change of those parameters, which each of them can easily estimate by the temporal axis pattern of here's a change coming from this machine, here's a change coming from this machine, so what's the average rate of change, and send that rate of change back to everyone that holds a copy, so that those caches have an expiry date with them, at which point they automatically fetch the latest value, so the algorithms don't diverge. And that's at the root of a lot of these distributed implementations. What I like about it is that we just had a picture of a statistical model, and that picture drove how you distribute the data, and it drove how you distributed the actual computation. And there's very few frameworks that really allow you to do that. Now that was the end of the dry part, so let's get to the juicy part. So one such application that I had the privilege to work on while at Microsoft Research is a system called TrueSkill, and that's joint work with Tora, Grapple, Tom Minka, and Phil Trelford. And the idea is that, or the problem first, is that you play a game. And so an arbitrary game has k teams, and every team has a variable number of players that are in them. So let's call them n1 to nk. So here's an example. You play a game of 8 players. So these are the 8 players. You know which team has won, in this case, the team with the higher score, the red team. You do know which player is associated with which team. But here's a different game, just to give you the variety. So you have 8 players now. They play in 8 teams. And what you know is the order in which each of the teams end. So in this case, this player happened to have the highest score, so that's why he's in position 1. That player at the same time had the second highest score. These 2 players were drawing, and these 2 players were drawing because they had the same score. So you want to have a system that basically gets fed data, which is how many teams, and which player is playing per team, and what's the partial ranking, or what's the total ranking of the teams that were participating. And what you'd like to learn is a single number for every player that's playing that game that has the semantic that if one player has a higher skill than another player, he's more likely to win if they were ever to be matched up again. That's the only semantic that's the minimum semantic that makes sense if you kind of build a model that you want to use for ranking people, because everyone wants to know who's the best. And for matching them, if 2 people are simultaneously online, or usually in popular games we have hundreds, thousands, to sometimes 1 million people simultaneously online, and knowing which 2 should now play with each other. So from a sort of data angle, you can think of it as it's a lot of partial orderings. So these four, and then these 4 played, and these are the same. Now you have to stitch them together. So there may be a few times that the better player lost, but that should be the unlikely event. So you have to stitch them in one total ordering. So simplest model is to say, well, we have 2 players, and they both have a skill. Let's say we even know the skill. So what's the model? What's a good model for a match outcome? Well, one good model could say each of the players' skill drives their performance. In fact, the performance is the mean of that skill. So the red player has a performance skill for this, and so the distribution of performance is somewhere Gaussian around this, and the blue player is somewhere around this. So jointly, between these 2 variables, S1 and S2, you have this nice Mexican hat. And then, again, one of the simplest model is to say, well, if P1 is bigger than P2, then player 1 wins. If P2 is bigger than P2 is bigger than P1, then player 2 wins. So what's the probability of this variable given those 2? In pictures, it's the area, the blue area versus the red area. So you can see in this case, red is more likely to win because his skill, the mean of that Gaussian, is a little higher. That's a simple model. That's actually the model that's used for chess ranking, ELO, originally, and then they changed. The only difference is that it changed from a Gaussian distribution to a logistic distribution. Now, how do we deal with 2 teams? So we have more than 1 player per team. Again, go with the simplest model that says 2 teams, the skill of the team, in this case the red team, is the sum of has a Gaussian with the sum of the skills as the mean, and the uncertainty of what that performance is actually multiplying by for each player. Same for blue. We already have a good model for how to combine 2 teams and their performances and translate that into a match outcome. So that's a relatively simple and additive skill model. Okay, what do we do with 3 teams? And so I pick a very generic part here. So 1 team with 1 player, 2nd team with 2 players, 3rd team with a single player. We can first use the same idea we used before. So in the model, we say that the skill of a team is the sum of the skill of its players, and the uncertainty grows linearly. So it's basically adding up for each player that's participating. But now with 3 teams, we have quite a range of match outcomes. In fact, 6. Okay, so the match outcomes is basically if in a random draw, T1 happened to be bigger than T2 and T3, then that's red wins over blue, wins over purple. But if T2 is bigger than T1 and T3, then blue wins over red over purple. So that's a lot of outcomes. In fact, for 3, it's only 6, but for 5, we would already be at 120. And so that's a sampling model that allows us to sample match outcomes. Now, here's the catch. I said before, what's the data? The data is not that we know the skills of people when they play online and we'd like to generate how they end up playing. The data is the other way around. we know what the match outcome is. We know that red won over blue and blue won over purple. So what we actually know is that T1 happened to be bigger than T2, and T2 happened to be bigger than T3. And now what you see is that this nicely, when you look at the picture, it's just, it doesn't have loops, it's just a tree. In fact, if you translate that into a vector graph, it means that we have a prior for this, prior for those 4 skills. We have a relationship that was a Gaussian between, this is a Gaussian relationship. This one was the fine threshold function we saw earlier, T2 less than T3, T1 less than T2. So if we actually just apply the rules that we saw before to Gaussians, we get an algorithm known as true skill. One way to reinterpret this is that the product, this is now for this particular vector graph, we see that we have in pictures shown or depicted a function that has 1, 2, 3, 4, 5, 6, 7, 8, 9 factors. But they have an interpretation. This is effectively this partial product of 4 is the prior. And this product of 5 factors, when you sum out those variables, it's effectively the likelihood. So you multiply this as a function of the skills with this as a function of the skills. It's known as Bayes' law. And so you should get, in statistics, the exact posterior. And that's what you get. You run this algorithm. There's one catch, little catch, which is those thresholds. We had that before. They're not exact, so you have to iterate on them. So basically iterate back and forth the update equation by constantly fitting. This is a truncated Gaussian, so you make it a Gaussian again. This is a truncated Gaussian, make it a Gaussian again. Truncated, truncated. But in practice, you do this 3 to 4, sometimes 5 times, and it converged. Okay, so if you do that, you still, what you have in terms of gaming is you now have a system that you can feed match outcomes, who played in which team became first, second, third, and fourth, and it computes you in a database. If you have a lot of games, you have to distribute this. It computes you the skills for those, meaning a mean and a variance for every player. But how do you combine them if you wanted to rank them? So what you need to do in order to do that, you need to make a decision. And when a system makes a decision, it can make mistakes. So the kind of mistakes that it can do right now is it can either rank a bad player, a truly bad player, too high, or a truly good player too low. So which of the two do you think is worse? Would you optimize for? Would you say, I don't want that? Would you rather not have a bad player on top or a good player at the bottom? So leave them at the top. Okay, any other votes?
You probably get more money from good players, so yes.
You'd leave them in the top. Okay. Any takers for putting a?
So what I believe, one explanation could be if you had a bad player too high, then you would annoy a lot of good players they're near to.
Mm-hmm.
You would annoy one good player by putting them too
Yeah.
low.
Let me ask you a different question. Probably that answers this first question. Who's currently the fastest racing driver? Happens to be a Brit. So who's currently the fastest racing driver in Formula One? That's right, Lewis Hamilton. Very good. And who's currently at 16th position? See, most people know the top of a leaderboard. That's where they want to see truth. If there is a little mistake done by putting a good player down, that is forgivable. But if you put, I don't want to insult people now because I'm recorded. But if you put a racing player that's not so strong as Lewis Hamilton at the top, then I think people would not believe in the ranking system for racing. So what we optimized for is making sure that the top of a leaderboard is accurate at the expense, of course, that some good players may be ranked too low. It's called quantile loss. So if you do that, you end up with a function that you minimize, which is if you take the quantile of that distribution, you end up minimizing this sort of asymmetric loss function. When you look at it, if someone is truly good and plays few games, his uncertainty is large, so he has to reduce it. But he can always get that down by playing more or racing more or participating more in games. For matchmaking, it's a different criteria. You can't just match people by this, because for matchmaking, you want games that are fair. So a fair game is a game where I don't know the outcome up front. So if I match two people, they should pretty much have a balance. They should have a match that is where the outcome is, where their performance is as close as possible to each other. And in fact, that's the criterion in true skills. So we basically say, compute the probability that two players have the same performance, given their difference in performance and their sum of uncertainties, normalized by these are the same players. So there's no difference in mean, and there's no uncertainty about that difference. Okay? So if you take that to its limit, so this is a bit vague here, you get a matchmaking criteria that actually optimize for good matches. And so we tested this on a publicly available data set. It's actually what triggered this research and this application of a graphical model in the first place. It's an internal beta of Halo 2. And so if you use the old system, which is much more like a maximum likelihood version of the system I described before, where we just do maximum likelihood, which is maximizing this first equation, you see this is the two best players printed over a number of games they played, their sort of performance level. And one thing that's stunning about this is even though the blue player is in absolute terms 10 levels higher, he somehow seems to get there slower. So per game, he seems to be, as an estimation, you would estimate, well, if this guy played 400, he's probably better. You feed the same data in the system that tracks the uncertainties at the same time, a probabilistic model. You get something that reverses, but also you get it very, very fast. And you can actually show, and we've done a lot of simulations, that if you see this as an encoding game, where you try to get the permutations of n players, which takes you n log n many matches of two players you need to play, this system comes pretty close to this information theoretic limit that you have to do, meaning the absolute minimum number of games that you need to play. Now, was this a correct statement? Well, there was a bug in the system when it was a beta, and so these two people did actually play against each other. What you see printed here is the predicted probability that red wins, blue wins, or they draw. These are the two players that we just looked at before. In this instance of time, they did play against each other, and that was the empirical ratio. So that gives a little bit of evidence. But is there better evidence? And there is indeed. So I think everyone here in the room knows Halo, so I want to just get to this graph. If not, I can show the video at the end. So what does this graph show? So this graph is basically going from anecdotal evidence. So what we saw before was two players that happened to be playing a lot or playing very strong, and by a bug playing 8 matches, and now it matched just in one instance of that graph, to 1.3 million players in a beta of the next version of Halo, Halo 3, playing for 6 weeks, also a beta. This was a public beta. And what we recorded is for each of the 1.3 million players, we recorded after they've played one game, and everyone played, of the 1.3 million played one game. What's the fraction of games that they lost? What's the fraction of game that they won? So you can either lose your first game or win your first game. And the bubble shows, of course, the first game they were all at level 1. So if I click advance, what's going to happen is that it's going to filter more and more that data set of 1.3 million players playing 300 matches down, because not everyone played 2 matches, not everyone played 3. Less and less people actually played 100 matches in this beta, or 150 games in these 6 weeks periods. So in the end, we're looking at a bubble plot of only 3,000 people of the 1.3 million that played more than 300 games. And for each of them, we see on the y-axis their estimated skill level, and on the x-axis, we see the ratio of n games that they won. So if this is a very good ranking system, what should you see in the end? I'll give you some alternatives. Should you see a straight line, diagonal line? If we see a diagonal line, what does that mean? It means that we have players that are very low skill, estimate high skill, and those of low skill lose all their games, and those of high skill win all their games, and those of average skill 50-50. Is that a good experience? Well, I guess it's a good experience for those guys, but not so much for those guys. So how would if you were to know everyone's skill, how would that graph look like? Gaussian plot?
Well, maybe it tells for 50%.
That's what it should be, right? Regardless of how good you are, you should always get the player that kind of makes you struggle for a win. So you should get this thing. So let me just start the movie. So what you see here now is actually this very effect playing out. So you see all people that played 60, 70 games. So now we're at 100 games. So now we're already down to a few 10,000 people that played so many games in the 6 weeks. And we see that this curve starts to line up. It took about 100 games for someone to reach level 50. That was by design, because the system was so fast that we had to introduce a noise term into the likelihood to slow it down in a controllable way. And then eventually you'll see it almost peaking almost doing a bar at 45. The reason is that we had a 5% chance of drawing in these games. You run out of time. This is a shooter game for those who don't know Halo. And if you run out of time, it can be that 2 teams draw. But the nice thing you see is there's not a dot omitted here. You see that there wasn't a single player of those 3,000 that played a lot of time that won more than 75% of their games. There wasn't a single player that lost more than 75% of their games. So no one really got a terrible experience. The winners had to fight for it, the skilled, I should say, the skilled people had to fight for it, and the not so skilled people got matching opponents given to them. Maybe there was a streak of 5 to 10 games in there. It's actually interesting when you launch something for real, and then someone does spend the whole evening losing. They'll blame science and everything to be wrong. But you look at the data and you see, yeah, there is streaks of 5 to 10 games losing in there, but on average, it works out. Good. Just before I move on to the forecasting problem, one interesting thing we did is after we've done the analysis, we thought, well, wouldn't it be interesting to do an analysis where we compare the skills of chess players, but we go through time? Because chess is usually only played forward in time. So what I mean by this is, chess players have their skill estimated to have a good opponent in the next match. The same way that I think people wanted to understand this, is AlphaGo as good as the best player, or a little better, or a little worse? Who'd be the best opponent for the system and with them? But what usually isn't done is going back in time and revising in light of future information, how strong was the player, so we can compare people across time. So the way we did that is that we built a graphical model where we had the skills of a player, but now per year of their active life. And then another player they played against in a tournament. So this is the other graph that you saw before, 90%. That would mean in this match, they had a particular performance, and then one won or the other. In this match, they had a particular performance, another outcome, and one won or the other. But then from year to year, we created a new variable, which is we remembered everyone's skill and didn't just go forward in time. So we end up with 20 million variables out of this 3.5 million professional and semi-professional chess game database. This is work back in 2007. There's a lot more games these days. And 40 million factors. So at the time, we could still compute this in a single machine. So today, this should be easily doable. We fit this in 11 gigabyte of RAM. Didn't need to distribute. And so what's nice about it is you can now run this, and you run basically the message passing, send this message, then iterate on all the players in that year, send this message, that message in this year, and then go back in time, send this message, and keep iterating the years, and then forward and then backward. About 5, 6 iterations, and the system converges. What you get now is a skill curve for what I'm plotting here is the best player in each year, and then their entire life trajectory. And so this is actually starting from professional chess in 1850 to 2006, what apparently is the estimated best player. I think the popular names pop up. I mean, those the usual suspects, Garry Kasparov and Bobby Fischer. But what's nice is you can now really compare how would a Steinitz have played against Karpov. He could never play. I don't think they had an overlapping year of life. The other interesting thing you see, you're looking at the top of the curve of skills. So there's this year there's another 200,000 people that are way below. So the average is actually decreasing because in around 1960, the semi-professional players got introduced into this data set. And so you're really looking at the top of this, sort of the highest skill. But what's interesting is this year. So why is there a sudden increase in playing strength by about 200 to 400 points? Can people pick a guess? 1980. Those that haven't seen the talk. See Zubin grinning. Why would people get suddenly stronger?
Wasn't the miners strong?
It wasn't what?
That's a British reference.
No.
84.
Computer chess, yeah. It was computers. So introduction of computers that people could train against. And that really upped their game because before people had to travel to play against the best, and they had probably 3, 4, let's say 10 opportunities per year, and that was the amount of training they could get against the people of same playing strength. The other interesting thing is if you plot the uncertainty, you see something very intuitive, which is if you have no constraints, because it's the first year of someone's professional chess life, or the last year of someone's professional chess life, you have more uncertainty because it's just less constrained that way. And usually it gets more accurate towards the middle of the sort of professional career period because it's more constraining when you think of it as a time series. And the time series aspect is also a good intro into the second set of applications for graphical models. How do we do in time? Yeah, let me skip that one then. You can talk about that one if you're interested in another application. So the problem we worked on since 2 years is one of predicting the demand of fashion, as I said earlier. And so by fashion, I mean apparel. So this is a shirt, shoes, jewelry, watches, jewelry, and luggage. So these are the things. And what makes this problem sort of big is that this happens in 7 different marketplaces: Germany, Italy, England, US, France, Japan, and Canada. So in each of them, you have about 5 million things you need to predict for, and you have about a history that goes sometimes back to 3 years. So this is called a history, and you have for every single day, we call it an ASIN day. So an ASIN is a standard identifier for a product, and a single day of performance is, a single day of demand forms an ASIN day. So with 5 million things and a year, 3 years of history, you end up with about 4.5 billion training examples to learn from. Every single day, a few million get added, about 5. What you need to learn from is, what's this curve looking like? Now, unfortunately, if you look at the statistics of this curve, so this is the histogram, just how many, if you just go over the entire 4.5 billion, you have 98% of days where products don't sell anything. And then you have a small percentage where products sell probably 1 unit. And then you have something that probably has a smooth decay. So the kind of model that we chose is reflecting that. Because what we need to model is, what was the observed number of units on a day for product I? And because of this massive skew, what we found is that classical models like Poisson or negative binomials don't really describe that. And so if you go to higher counts, 2 is usually sufficient, you do get a good fit. So if you sort of put this in graphical model terms, what we have is features, observations about the products, their color, which particular day of the year was this relative to the marketplace. So Thanksgiving in the US is a big day. It's not such a big day in Japan. I think it's also not such a big day here. Maybe Valentine's Day, Halloween starts to become a big day here, but probably not as big as in the US. So these are all features. Time. Was the product promoted that day? Did it got like 1% of all time it was on the front banner of Amazon.de or Amazon.com? All this information is described in a feature vector, and you'd like to explain how the observed number, 0 mostly, of units sold in that day. So the simplest model says, well, we do a model where we say we have a latent variable. Let's say this is the Poisson success rate, and then the success rate of the Poisson influences the number of units, or if you simply want to describe. In fact, if you want to describe 0 or 1, these are simply the log odds of a process that rolls out. Yes, it's 0. Yes, it's 1, or it's the success rate of a Poisson. Okay, so the simplest way we can treat this is day by day. Now, this is probably not as accurate in particular because there's a time series aspect. Things develop over time. So one way to extend that is to say we have some latent effect that we can't observe. So this is describing the effect of having 1 unit or more, 2 units, 0 or more, 1 or more, or 2. And the latent effects are influencing how the time series progresses. So meaning this latent cause, a bit like the skill over time, influences this latent cause. So what I incrementally built here is sort of a graphical model of a time series where you have a multi-stage likelihood. By multi-stage, I mean a likelihood that very much models the fact that you have an exorbitant amount of zeros and ones captured by those Bernoullis, and then a parametric process like a Poisson for higher counts, and a time series, a latent state time series model. And so when you put this together, I just want to give a few examples how that looks. So let me skip this. And so you take this is actually something that sells a lot. So this is rare. So this is an actual number of units over a period of a single year. So this starts in 2013 October, goes to 2014 October. if you were to do the model where you treat them independently, one of the problems is that you get more and more certain as you get more and more data. But typically, as you go more and more into the future, you don't get more certain. You usually get less certain, right? So this model doesn't model uncertainty as it evolves over time. And so if you just shoehorn this problem day by day, you say I have 4.5 billion observations and I disregard the time component, you get a prediction that gets the error band. So the error band is, think of it this way, is the cyan and the green curve, so they're sort of a quantiles of the distribution. You see that they get narrower and narrower as we go towards the end. If you do use a latent state, but you don't take care of the multi-stage, so you shoehorn a Poisson over this, you get something that gets exorbitant uncertain as you go into the future. And if you do describe the zeros correctly, you get something that, yes, it gets more uncertain, but it kind of doesn't go out of band. And the other advantage that this model has is that it allows you to deal with out of stock, and that's an actual practical problem. So what you see here is in red below the days where Amazon hadn't stocked enough of those. So all you observed was that the demand was that number or higher. Like you just don't know. There was nothing that you could sell anymore. Possibly you could have sold more. If you treat out of stock as zeros, what happens again is that you get very certain that this is zero. So if you make predictions, you basically have an underbias, and you also get far too certain about the value zero because that wasn't what was observed. If you didn't observe it because you ran out of stock and you treat in this graphical model the z's not as something observable, but as something unobservable, so you sum over them, what happens is the right thing, which is that the model gets more uncertain over days where it didn't know the demand, and it doesn't get biased towards the future. So you see the particular other product here, because it didn't take the zero as an indication for the demand was nothing. It was simply didn't take it as we didn't know, because we for that period we couldn't restock. And what I described here to you is what is actually used since a couple of months to actually buy those 5 million things in all those 7 marketplaces. So I think the kind of things I want to conclude on is probabilistic models are incredibly powerful to describe real data processes. I hope I convinced you that there's easy models to describe how people play against each other, how skill drives that, how demand of fashion can be described. The factor graph as a pictorial framework of probability theory is actually a very nice bridge between statistical models of data and the computation that results if you want to answer questions about that data. And that large-scale approximate inference isn't just a theoretical tool that's kind of nice to think about, but it's something incredibly practical. So TrueSkill has tens of millions of sessions that are getting matched, and hundreds of millions of people have actually been matched across all Xbox Live games. And fashion articles is something that I hope most of you go shopping every day on Amazon. And if Amazon does a good job there, prices are going to be low. Thank you.
Thank you, Ralf. I guess we can take questions both from the audience here, and Jared will be watching out for questions from live stream. Anybody like to start? Okay, I guess I can ask you one.